Hello everyone, welcome to problem solving tutorial. This is me Mahir. Today will be in our last tutorial we saw the basic technique of sieve of Eratosthenes. Today we'll be going into the coding part. In our last tutorial we have come to know about four techniques. At first, the first one is we have to go up to square root of a number if you want to check that a number is prime or not. Then to mark each and every number previously whether it is prime or not, we have to start for the prime marking from square of a prime number. That is, we will start with a number and we will start marking the non-primes starting from the square of that prime number. Then we will increase by double of that taken prime number. That is, if you start with 3, then we will take 3 as prime number and we will start from square of 3, that is 9, and we will increment from 9 by double of 3, that is 6. And from 9 we will go to 15, and from 15 we will go to 21, and so on. And then we will mark the products. That means for each prime number we will keep marking their products as non-prime number. So let's go into coding. So at first what we need to do is we'll do the whole procedure in a function called sieve, which should be of type void. Since we don't want to return anything, it will be void, and this array will basically keep track of whether a number is prime or not. So basically its size will be the number of integers that we want to check if they're prime or not. So let's say 10 to the power 6, we will check up to 10 to the power 6. So for each of those numbers there will be one index in this status status array, and initially they will all be 0. That means they will be counted as prime. So for 0 they are prime, and for 1 they are non-prime. So initially all of these numbers are primes. So like we said earlier that number 1 is not a prime number since it has only one factor. Similarly, number 0 is also a non-prime number since it too has only one factor, that is 0 itself. So we will make the status of 0 and 1 to 1. That means they are not prime. So they won't be prime. Now we know that for all even numbers are non-prime, since except for 2 all even numbers are non-prime, since they are all divided by 2. So they all have 2 as a common factor of them. So they can never be prime number, since prime number can't have any other factor rather than that number and 1. So status of 2 is already 0 since we are declaring status array globally, so they will initially be 0. So we don't have to make status of 2 to 0 manually. So we'll start from 4 and we will go up to sz, since we are marking up to 10 to the power 6 and this loop will increment by 2, since from 4 we'll go to 6, from 6 we'll go to 8, and so on. So status of I will be 1. So we have marked all the even numbers as non-primes. Now what we'll have to do is we have to take care of the odd numbers. That means starting from 3 we will increment by 2, increase the iterator by 2, and from 3 we will go to 5, from 5 we will go to 7, and so on. For each of those numbers we will at first check. So let's come here. So at first, okay, so for each of those numbers at first we will check if it's prime or not. If it's prime, then we will start the marking, and we will mark up to square root of the square root of sz, since we know that after sz there will be no such number which hasn't been marked before, which can't be found by multiplying any of those previous factors. If you get confused, you can take a look at the previous tutorial that we have made on prime generation. Okay, so we will start from 3 and we will go up to square root of sz. So this is basically a built-in function of C that returns the square root of sz. So we will go up to square root of sz and we will I will increment by 2, since from 3 we will go to 5, then 7. Only the odd numbers will be taken into account. We don't have to worry about the even numbers since they are already marked as non-primes. Okay, now here's what might create problem. Every time we are calling this built-in function, it's gonna take some time, and it's gonna take a lot of time, which might cause us getting into trouble and get a TLE verdict. So what we can do instead is do this. This is actually the same thing what was done before. It's like I is equal to root over sz. So we are using squares of both left hand side and right hand side. So we are getting, in left hand side we are getting I square, in right hand side we are getting sz. So basically what we are doing is we are running a loop that runs from 3 to square root of sz, and it will increment by 2. Now what we will check is if status of I is equal to 0, that is if I is a prime number, then we will start from, okay, so far this part is done. We will go up to square root. We are going up to square root by this. I square is less than or equal to sz is equivalent to I is less than or equal to square root of sz. So we are going up to square root. So first one is checked. So the second part is start the prime markings from square of a prime number. Okay, so we will start the marking from square of a prime number. Here are two things. At first, square of a prime number. So how do we find out if I is prime or not? We just check if status of I is equal to 0, that means I is a prime number. So start the marking now. So we have sorted out the prime square of a prime number part. We know now that I is prime number if status of I is equal to 0. Now we will start from square of that prime number. So j will be equal to square of that prime number, and it will go up to sz, since we will be marking up to the last of our range number, that is the sz. And so this part is done. We are going up to square root and we are starting the prime markings from a square of a prime number. if I status of I equal to 0, then I is a prime number, and we will start from square of that prime number. Now the third part is we will increase by 2 into that taken prime number. Here the taken prime number is actually I, since status of I is equal to 0. So we will increment the value of j by 2 into I, that is 2 into taken prime number. So it will be 2 into I. For each of these numbers we will mark them as, here is, so third part is done, we are increasing by 2 of that taken prime number. Now the last part is we will mark the products as non-prime. So we will mark the products, that is the j's, as non-prime. I mean they won't be prime numbers anymore. Okay, so now that's basically all for marking the prime numbers as primes and non-prime numbers as non-prime. So basically what we are doing is, at first we are marking 0 and 1 as non-prime, then we are running a loop that goes from 4 to the sz, and it's incrementing by 2, and we are marking all. Basically what's happening here is we are marking all the even numbers as non-prime. Then we are start running a loop that runs from 3, the first, after 2 it is the first prime number, and we are going up to square root of az, and we are incrementing by 2 since all the odd numbers will be counted, since events are already marked as non-prime. Then we will check if 3 is prime or not. If it's already been marked as non-prime, then we don't have to go for it anymore. But if it is a prime number, then we will start from the square of that number I, and we will go up to sz, and we will increment by twice of I, and we will mark each of those j's as prime number. So after all this procedure, the status array will contain the information of whether a number is prime or not. If its value of a index is 0, then it is prime. If it's not, then it's not prime. So let's find out. Run a loop that runs from 0 to sz. Now what we will see is, if status of I is equal to 0, then we will print those numbers. They are our prime numbers. So let's run the loop and see for ourselves whether it's giving us the correct prime numbers list. Okay, so there are a lot of numbers, turns out, and it's not stopping. Let's just so let's write those numbers in a file. Okay, let's reduce az to 100. Let's print all the numbers that are all the prime numbers that are lesser than or equal to 100. So basically what we're doing is we're running a loop that runs from 0 to 100, and we will check if for any number status of I is equal to 0, then we will print them as prime number, and if it's not, then it will be completely ignored. So there's something going on with my compiler. Just paste it in another file. Let's name it says anything. Let's run. So what's happening here is that we are not getting correct output, so something's wrong here. let's just ignore it. So what's actually happening here, what I have done wrong is actually we haven't called a function yet. That means, yeah, we're doing all those markings and everything inside this C function, but we haven't called that in our main function yet. That's why we're getting funny outputs. So let's call the function and run it again. And again my compiler is betraying me. Well, here it is. This is the list of all the prime numbers that is lesser than or equal to 0. So let's do that again for AZ. Again, it's causing problem. Let's paste it in another file. Should be stopping anytime soon. It's a long list. Let's check. So here it is. These are all those numbers which are lesser than or equal to 10 to the power 6 and which are also prime number. Any number that you see here is a prime number. So that's all for now. This was basically implementation of Sieve-Eratosthenius algorithm that we have learned in the previous tutorial. So thanks for watching.